Welcome back to week 1, video lesson 2, which is section 11.1, circumference and arc length. As I mentioned in the last video, these first couple lessons are really designed to help you get a foundation of some very essential tools that will help us talk about area as we move forward. One of the tools that we're going to need to establish before we start talking about area is going to be the idea of circumference and arc length, which are ways that we can talk about the relative size of a circle or the distances around a circle in another way besides radius, which you're probably very familiar with. All that to say, we'll go ahead and jump in, and hopefully by the end of this lesson, you'll feel comfortable enough with these ideas of circumference and arc length that we'll be able to take them and apply them when we start talking about the area of a circle. Now, a quick reminder for those of you who have since forgotten, circumference is the distance in one complete pass around a circle. In other words, the circumference describes the distance that you would need to travel if you were to go one complete revolution around that path of the circle, okay? And so that is primarily what circumference is going to be involved with. Now, what's interesting is that what we find is that the circumference of a circle is directly related, maybe unsurprisingly, to the total diameter of that circle. Right? Because the diameter of a circle is constant everywhere in the circle as long as we're passing through the middle. And so that diameter is going to stay fixed. And what we're going to be able to do is calculate how far we would travel given a fixed diameter when we also account for one other thing, which just so happens to be what's called pi. Pi, which you've seen represented as 22/7, is an approximation. Or you've also seen the approximation 3.141592, probably just the first few digits of that. But pi, this is a special and irrational number that relates the circumference and diameter of all circles. So what's interesting is that this irrational number pi is a value that is exactly representing the size at which how much bigger the circumference is relative to the diameter. So the diameter of a circle is always, if you multiply by the value pi, going to give you the circumference. In other words, the circumference is pi times bigger than the diameter, which is something that you can see reflected in the formula for circumference here, which is pi times diameter. So again, you'll see this here. Circumference is pi times diameter. Diameter is two radiuses, right? It's all the way across, not from the center to the edge. So if you see it written like that, then you'll see it written as 2 pi r. Again, both of these are saying whatever the diameter is times the scale factor of pi, that is going to generate for us the distance all the way around, okay? And again, we can kind of use this in practice. So if somebody said to us, hey, I have a circle that has a radius of 9, and again, to see what that looks like, we can draw a circle, we can draw ourselves radius 9, and we want to know what the distance all the way around the outside is, right? This is our circumference that we're curious about. Oops, not make that a pentagon, but we want to know that circumference. What we're going to do is first determine the diameter. Well, the diameter of our circle would be 18. And then pi is the scale factor of change between the size of the diameter and the size of the circumference. So the circumference would be 18 pi. Now again, we could throw that in a calculator to get approximately what that is in centimeters. But again, this is an exact representation of that here. Great. Oops. Let's try again. Cool. Again, we can work backwards too. So if someone says, hey, it just so happens that the circumference of this circle is 50 pi inches, we can say, well, the transition between diameter and circumference is a factor of pi. If I'm going from circumference, which is the larger measure, to the diameter, which is the smaller measure, I need to divide by that factor of pi, meaning that my diameter must be 50. And therefore, my radius is 25. Cool. Again, you might have non-exact answers. So again, someone could say, hey, I have a circumference of 50 inches. Again, same process. If I'm going from circumference to diameter, I divide by a factor of pi, meaning that 50 over pi is my diameter. Or again, 25 over pi is my radius. So again, this nice relationship that's modeled by pi allows you to find these larger distances around the outside of a circle. Now, the reason this is primarily helpful is to introduce the idea of arc length, which is to say we could look at a circle such as the one I've drawn right here, and we could maybe investigate just a part of that outer shell. So I might want to know not the distance all the way around a circle, but the distance from some starting point to some ending point on the circle, right? Because maybe this represents a path that we're running around a circular track, or, as you'll see the connection to area, it might be a relevant slice of a pizza that we want to consume. And we want to know how much area is in that slice of pizza we're going to eat, which isn't the whole pizza. It's just a section, a sector of that pizza. And so now that we have the idea of circumference mastered, we can start talking about the idea of a part of circumference, which is also called arc length. So what does that look like? Well, first off, there's a little error here in this PDF, and I apologize. You will always see things written. So if we're talking about circle, an arc length of circle, or from A to B, we'll kind of draw with a little arc on the top. So we would say the measure of A to B, like so. And essentially, all that we're doing when we talk about arc length is talking about a proportion. We're basically saying, how far is it from A to B, which is this top part right over here, compared to the whole distance all the way around, which is this bottom part, the circumference. And then in order to set up a true proportion that we can solve, we need to know another ratio. Well, the other ratio is to say, what is this angle compared to what is the total angle all the way around? And the nice thing about a circle is that's always going to be 360 degrees. So we're basically saying the ratio of how far we travel around the outside compared to the whole thing will be the same ratio as the angle of that arc compared to the whole thing of 360, which gives us a really handy proportion that we can use at all times. To show you this in practice, again, I'll kind of come down here. Someone say, hey, what's the length of arc length P to R? They want to know how far we travel if we walk from point P to point R along the outside of the circle. Well, again, I'm going to set up a proportion. I'm going to say PR, that arc, is some proportion of the total circle. Just like the angle of PR is proportionate to the total angle excuse me, of the circle. Excuse me. Well, what do we know? Well, we don't know the arc PR. That's in fact what we are asked to find. We don't know how long it is to walk from P to R. But we do know how far it is all the way around, because the diameter of our circle, if we look up here, is going to be 24 inches. So the circumference, which is based on the diameter and then affected by a factor of pi, is 24 pi. So whatever the arc is of PR compared to 24 pi, that is going to be proportionate in the same way that the angle components are. That 100 degrees as compared to the total circle, 360. And you'll notice by setting up a proportion, it's now incredibly easy to solve. To find the length of PR, you multiply by 24 pi. Multiply by 24 pi. Notice we have degrees in the top and the bottom, so we're just in normal units at this point. And again, I have that the arc of PR is going to be 2400 pi over 360. Throw that in a calculator, and we're good to go. So again, all that arc length is it's a proportion. It is a certain percentage or a certain size of the whole thing. To give you another example, let's say we have a similar problem, but we are told the arc length and we want to find what the whole thing would be. Well, notice our process is exactly the same. We're going to reference this red equation on the left. We're going to say, what's the length of the arc we're investigating? Well, we know the length of arc QR. That's 6.5 meters. Compare it to the total arc length all the way around, known as the circumference. Well, we don't know the circumference, so we'll put a variable c. And then, just like the other equation on the left, we're going to say, well, given that PR is 6.5 meters, that's how far it is to walk, QR, to walk from Q to R. What angle determines the size of that path? Well, that's 130 degrees. Out of a total of how many? What would the whole circumference have as its reference angle? Well, 360. At this point, we would go ahead and likely flip our fraction so that our variable's not in the bottom. C over 6.5 is 360 over 130. And then at this point, we would multiply both sides by 6.5. We'd throw that in a calculator, and that right there would be the answer for the size, of the circumference. Let's see if I can get a better box this time. Great. And again, notice we could use this process in order to find the angle as well. So I'll just set this one up. But again, the whole idea is if you know a part reference to a whole, you can set up proportions that work. So I could say, for example, hey, look, JK, that part I'm interested in, that arc is 21 meters. How does that compare to the whole thing? Well, the whole thing, let's see, we're going to have to do a little bit of math here. Our whole diameter is going to be 28.64. And again, the factor of change is pi meters. Great. And that's going to be equal to, again, my part, the angle of my part, which I don't know. So this is going to be the measure, the measure of arc JK. I want the angle measure of JK compared to the whole 360. Again, solve for the only thing that's unknown, which in our case is the angle of that arc. So again, just proportions. Now, where can you use this that's actually really relevant and helpful? Well, one place is to talk about when you're working with wheels, and especially if you're working with a model or a full-size car. So for example, it might say, hey, we have a wheel in a toy truck, and it is 4 inches in radius. So we want to know how far that wheel is traveling as the wheel is turning. So if it does 7 complete revolutions, how far will the car have traveled? Well, notice, in order to know how far the car travels, we need to know, in this case, first off, how far it travels in 1 revolution. In other words, we need to know 1 circumference. So if we were to solve a problem like this, we would want to set it up and say, well, first off, what's our circumference? This is our goal. We need to know how much the circumference is to know what 1 revolution is. And we say, okay, the radius is 4 inches. Well, what that means is that the diameter is 8 inches. And again, as we looked at earlier, we know that the connection between the diameter and the circumference, the scale factor is a factor of pi. The diameter is the smaller measurement of the two, so I multiply by pi to get my circumference. So I know that I travel 8 pi inches with every revolution. But I don't want to just travel 1 revolution. I want to travel 7 revolutions. So what I need to do is say, let's multiply this by a factor of 7. I'll get 56 pi inches is my total distance. But I don't want to be in inches, I want to be in feet. So I'm going to take this 56 pi and divide by 12 inches in every foot to get the number of feet. And that will be some answer. Again, I'd throw that in a calculator, and that will tell me how far approximately that wheel travels when it makes 7 revolutions. I think it's somewhere between 18 and 20 feet, which is pretty crazy if you think about it. With a toy truck with only that radius of 4 inches, 7 revolutions, and it's traveled 18 to 20 feet. Pretty wild. Okay. Again, another place you might see this is talking about something like a track. So if we look at something like a track, we might see something like this, where we want to know the radius, we want to know the distance that a runner's going to run if they run around the track. Now, you'll notice this is kind of a funky track in a sense because it has one edge, notably this edge over here, that's a larger curve than this edge is here. Slightly different configuration, but maybe had to be constructed that way due to the terrain. And so we want to know how far that runner is going to travel as they run around the track. Well, first and foremost, we can start plotting this and thinking about this in pieces. We know the runner is going to run one straightaway here. And we know to get to the curve. And then we know on the back side, they're going to run that straightaway again. So we know for a fact that they're running 84.39 meters twice. Cool. Then they get to these curved parts, which we're told have an angle measure of 180 degrees. In other words, this is a semicircle, right? Half a circle. Oh, you can definitely not see that green on there. Okay. But we've got one semicircle here and one semicircle there. Cool. So we need to figure out the distance they travel on each of these green areas. Well, in order to find, let's say, green area number 1, we're just going to need to set ourselves up a proportion dealing with the arc length. We know that this is 180 degrees out of the total 360 that this runner is going to be traveling as they run along this curve. And we know that we want to find what that arc is. And the measure of the arc is relative to how large that would be if we were to travel all the way around. Well, what's the circumference of this? Well, again, we know the radius of 36.8. To find the diameter, we double that. We get 73.6. And then to get the circumference, we multiply by a factor of pi. So this right here describes path 1 over there. And again, we can solve this, multiplying both sides by 73.6 pi. Great. That, whatever that number is when I throw it in a calculator, will tell me the distance we travel for arc 1. Now we can travel to arc 2 and do the exact same thing. We can say, look, it's a 180 degree turn to go from one side of the curve around the track to the other out of the 360 in a circle. And again, we want to know the length of that arc when we compare it to the 88.04 pi circumference that circle would generate. We solve that equation by getting arc by itself. And then we will have an approximation for that measurement over here, section 2. After we've done that, quite obviously, we're going to add section 1 with the 84.39 of that straightaway, plus section 2, plus the 84.39 of that straightaway. And again, now we have the entire distance around that track. So you'll notice when we see objects that are constructed of partial circles, such as pill shapes or track shapes as good examples, we can use the idea of arc length to help us break them down into more manageable process. Now, the last thing that we'll talk about, and I believe this is the final thing on here, is the difference between radians and degrees. So I mentioned in the last unit, you wanted to make sure your calculator was always in degrees. And it made sense because most of our angle measures in triangles were measured in degrees. But in a circle, we now have the opportunity to measure things in terms of radians. What radians are is this is a measurement of an angle relative to a circumference, 2 pi, instead of a degree, which is out of 360 degrees. So we can convert back and forth really easily between radians and degrees if we ever needed to, by just keeping in mind that 2 pi and 360 are our all the way around measurements. And so if somebody says, what's 60 degrees in radians? We say, well, what's 60 out of 360? Whatever that is, if I multiply that by my goal of 2 pi, I want to be in radians, which are measured relative to 2 pi, that will tell me what it is in radians, which in this case is going to be pi over 3. So that is an angle measure. Pi over 3 radians, which is kind of like saying pi over 3, or kind of like saying like 20 degrees. Again, it's a measure of how far around a circle you're traveling. And again, same process over here. If somebody says, hey, we have 5 pi over 6 radians, we say, well, what would that be given that I'm comparing to 360 degrees now? Again, we multiply and we end up getting some horrible number. Yeah, it's a number. It's a thing. Okay? So that's really how we're going to travel between the two of these. And again, you'll notice these here allow us to move between those two measurements. So again, it's somewhat handy to keep that in mind as we're going about things. So anyhow, with that all said, oh, sorry, I did catch a mistake. 5 pi over 6 over 2 pi. We have to do our part out of our whole times 360. But anyhow, that is how we're going to be able to talk about the angle measures in circles, not just using degrees as well, which will be a handy tool we'll see when we talk about area and sectors, where it can be a little bit easier since everything's in terms of pi already. But again, I hope this was helpful for you to get an idea, an introduction to the idea of arc length and circumference. Again, arc length is just a part of circumference. So really, an understanding of circumference and proportions is all you need to be successful today. Thanks so much for tuning in on Lesson 2. I'll see you for Lesson 3.